Now I am going to teach module 2 of chapter 2. This module is devoted to the theory of first order quasi-linear partial differential equation. We shall show that the solution of a first order quasi-linear partial differential equation is linked with the solution of a simultaneous equation, and that simultaneous equation is known as Lagrange auxiliary equation. We shall give the geometrical interpretation of a first order quasi-linear equation, and lastly we shall use these concepts to give or to solve some geometrical problems. So, let us go to the first slide of this module. Now, I am going to state an important theorem which says that the quasi-linear first order partial differential equation capital P small p plus capital Q small q equals to capital R has the general solution phi u v equals to 0, where u, which is function of x, y and z, is equal to C1, and v, which is function of x, y and z, is equal to C2, are solution of the simultaneous equation dx by capital P equals to dy by capital Q equals to dz by capital R. Here small p and small q are z del z del x and del z del y respectively. So, in this theorem we can see that the solution of the quasi-linear equation Pp plus Qq equals to R is involved with the solution of the simultaneous equation which is given in equation 1. Now, we shall first prove this theorem, then we shall apply this theorem to solve some mathematical problems. Now, u equals to xyz equals to C1 is a solution of equation 1. Therefore, if you take the total differential of u, you will get the relation ux dx plus uy dy plus uz dz equals to 0, and we also have that u equals to C1 is the solution of the simultaneous equation 1. Therefore, this equation ux dx plus uy dy plus uz dz equals to 0 and the simultaneous equation 1 are compatible to each other. Now, from the earlier side, since dx dy dz are proportional to pqr, so from this equation we can replace dx dy dz by pqr and we obtain the relation pux plus quy plus ruz equals to 0. In the similar way, taking v is equal to xyz as a solution of the equation dx by p equals to dy by q equals to dz by r, we can obtain the similar relation p vx plus q vy plus r vz equals to 0. Now, solving these two equations for p, q and r, we will get p divided by del uv del yz equals to q divided by del uv del zx equals to r divided by del uv del xy. Now, we have already seen in module 1 of this chapter that the relation phi uv equals to 0 leads to the partial differential equation p del uv del yz plus q del uv del zx equals to del uv del xy. Now, substituting the values of the Jacobians from relation 2, we will get that phi uv equals to 0 is a solution of the equation pp plus qq equals to r, and this equation is known as the equation, this equation means the equation 1 is known as Lagrange auxiliary equation. So, we obtain that phi uv equals to 0 is a solution of the quasi-linear equation pp plus qq equals to r, where these u and v are the solution of the simultaneous equation 1 which is known as Lagrange auxiliary equation. Now we shall apply the previous theorem to solve this mathematical problem. In this example, we have to find the general integral of this quasi-linear equation. Now we can write this equation in standard form as this, some function of x, y, z into p, and this is a function of x, y, z into q equals to some function of x, y and z. So, the Lagrange auxiliary equation for this quasi-linear equation is dx by capital P equals to dy by capital Q equals to dz by capital R. Here capital P is the coefficients of small p. For this example, it is small x into z minus 2y square, and capital Q is the coefficient of small q, which is for this example y into z minus y square minus 2x cube, and capital R is z into z minus y square minus 2x cube. Now, it is easy to find the solution of this simultaneous equation. If we observe this equation carefully, we can see that from last two equations, one can find the solution easily like this: dy by y equals to dy by z, and solving this equation one can obtain y is equal to c1 into z. Therefore, one can take an integral of the simultaneous equation u is equal to y by z equals to c1. Now, we need to find another integral of the simultaneous equation, that means the function v. For that, we need some manipulation of the simultaneous equation. So, we have done some mathematical formulas. We have manipulated this equation and we obtain an equation like this, which is written here: dx by x equals to d into y square minus z divided by y square minus z plus 2x cube equals to dw by w plus 2x cube, where w equals to y square minus z. And from this equation one can find an integral like this: 2x cube dx plus w dx minus x w dw equals to 0, and it can be solved. So, our another integral is x square minus w by x equals to constant, that equals to c2. Now, substituting the value of w from here, that means putting the value of w as y square minus z, we will obtain the value or the expression for v x y z as x square plus z by x minus y square by x square equals to c2. Therefore, the general integral is phi of u v equals to 0, where u is y by z and v is x square plus z by x minus y square by x square equals to 0. So, in this example, we find that the solution of the quasi-linear equation can be obtained from the solution of the corresponding auxiliary equation, and it is easy to find the solution of quasi-linear equation from the solution of auxiliary equation. Now the previous idea can be extended for n number of independent variables, and the corresponding theorem is stated here. If ui x1 x2 xn z equals to ci, where I equals to 1 to n be n independent solution of the equations dx1 by p1 equals to dx2 by p2 equals to dxn by pn equals to dz by r, where ci's are the constants and pi's are functions of the independent variables x1, x2, xn and the dependent variable z, and z is the function of x1, x2, xn, and capital R is function of n independent variables and the dependent variable z. So, the solution of the ui's are the solution of the simultaneous equation 4, then the solution of the quasi-linear equation which is written in equation number 5, p1 p1 plus p2 p2 plus pn pn equals to r is given by phi of u1 u2 un equals to 0, where these PIs in equation number 5, small PIs are the derivative of the dependent variable z with respect to the independent variable xi, I equals to 1 to up to n. Now we illustrate the idea for taking this example. In this example, there are 3 independent variables x, y, z and 1 dependent variable u. So, this is a quasi first order quasi linear differential equation and we have to solve this equation. So, the corresponding Lagrange auxiliary equation is dx by u plus y plus z. This is the function which is coefficient of del u del x, dy by u plus z plus x, this is coefficient of del u del y, and this is dz by u plus x plus y, this is coefficient of del u del z equals to du by x plus y plus z. And from these equations, simultaneous equation, one can find easily 3 integrals. Since there are 3 independent variables, for the general solution we need 3 integrals. So, from this equation one can obtain 3 integrals as x minus y by y minus z equals to c1, and the another integral y minus z by z minus u equals to c2, and x plus y plus z plus u to the power 1/3 into z minus u equals to c3. Therefore, the required general solution of the given equation can be written in the form some function of u1, u2, u3 equals to 0. So, this is our required solution. Now, I want to give geometrical interpretation of a quasi-linear first order differential equation. That means the equation capital P small p plus capital Q small q equals to R. I want to give how the solution of a quasi-linear first order differential equation is what related to a solution of simultaneous equation and what is the geometrical meaning of this relation. So, let us first take that z is equal to fxy is an integral surface of the given quasi-linear equation pp plus qq equals to capital R. Now, if we write the equation of the surface, integral surface in the form, in implicit form like fxyz minus fxy minus z equals to 0, then the direction cosines of the normal to the surface can be written as del z del x, del z del y minus 1. And with the standard notation, we can write the direction cosines are proportional to p q minus 1. So, in this equation, this p q, now look at the given equation p p plus q q equals to capital R, and this equation can be written in this way: capital P small p plus capital Q into small q plus capital R into minus 1 equals to 0. Now, if we observe this small p small q minus 1, this is the direction cosines of the normal to the surface. Therefore, this capital P capital Q capital R represent the direction ratios of some straight line which is perpendicular to the normal to the surface, to the integral surface of the quasi-linear equation. Therefore, the straight line having direction ratios p, q, r represent the tangent to the given surface. Suppose a particle starts from a point capital N and move in the direction p, q, capital R, then the curve prescribed by the particle lies on the surface, and for a given particular point M, the values of p, q, r is unique. Therefore, it represents that from through a given fixed point capital M, the integral, there is only one integral curve passes through that given point. Therefore, the integral curve of dx by p equals to dy by q equals to dz by r lies entirely on the integral surface of pp plus qq equals to r. or in other words, one can say that the integral curves of the simultaneous equation generate the integral surface of the given quasi-linear equations Pp plus Qq equals to R. So, this is the geometrical interpretation of a quasi-linear first order partial differential equation. Now, I want to mention here that for this quasi-linear equation we obtain a curve which is the solution of the simultaneous equation, and those curves are called characteristic curves. So, how can I obtain the equation of a characteristic curve? Suppose the equation of a characteristic curve is given in parametric form. That means x, y and z can be written as some function of parameter, a parameter small t. Then the tangent vector to this curve is dx dt, dy dt and dz dt. Since the tangent vectors, the direction ratios of the tangent vector is proportional to capital P, capital Q, capital R. So, dx dt must be equals to capital P, dy dt must be equals to capital Q and dz dt must be equals to capital R. So, equation 3 gives the equation of the characteristic curves of the quasi-linear equation 1. In the last section we have learned how to find solution of a quasi-linear partial differential equation. Now, we shall use that concept to solve some geometrical problems, especially we shall find the integral surface passing through a given curve, and we shall obtain or learn how to find the system of integral surface which is perpendicular to a given system of surfaces. Now, I am going to discuss how to find integral surface passing through a given curve. Suppose we have a quasi-linear equation Pp plus Qq equals to capital R, and u equals to C1 and v equals to C2 are the solution of the Lagrange auxiliary equation dx by p equals to dy by q equals to dz by r. So, the solution of the quasi-linear equation Pp plus Qq plus Qq equals to R is phi uv equals to 0, and we are interested to find the integral surface through the curve gamma. The equation of gamma is given in parametric form. X, y, z are some function of parameter t. So, u equals to C1 and v equals to C2 are solution of the curve. Therefore, u x t y t z t equals to C1 and v x t y t z t equals to C2, and where t is the parameter. And from these above two equation one can eliminate t to find a relation of the form phi C1 C2 equals to 0. Therefore, our desired solution or the general solution of the given quasi-linear equation is phi uv equals to 0. Now, I shall illustrate this idea taking one example. Suppose we want to find the integral surface of the quasi-linear equation 2y z minus 3 into p plus 2x minus zq equals to y into 2x minus 3, and the integral surface which passes through the circle z equals to 0, x square plus y square equals to 2x. Now, the auxiliary equation for the given equation can be written as dx by this equals to dy by this equals to dz by y into 2x minus 3. And from this equation one can find one integral u x y z easily as x square minus 3x minus z square plus 6z equals to C1, where C1 is a constant, and the another integral can be found easily dx plus 2 into y dy minus dz equals to 0. After integrating, v is x plus y square minus 2z equals to C2, where C2 being constant. Therefore, the general solution of the given quasi-linear equation is phi uv equals to 0, where the expressions for u and v we have already derived. So, phi of x square minus 3x minus z square plus 6z comma x plus y square minus 2z equals to 0. So, this is the general solution or the integral surface of the given quasi-linear equation. Now, we are interested to find that integral surface which passes through the given circle. Now, the equation of the circle can be written in parametric form as x equals to 1 plus cos t, y equals to sin t, z equals to 0. And if we substitute this parametric form to the one integral u equals to c1, it becomes 1 plus cos t square minus 3 into 1 plus cos t equals to c1, and v equals to c2, it gives 1 plus cos t plus sin square t equals to c2. Now, from these two equations, one can eliminate t and get the relation 2 plus c1 plus c2 equals to 0. Therefore, the equation of the required surface is 2 plus x square minus 3x minus z square plus 6z plus x plus y square minus 2z equals to 0, and this relation is obtained from 2 plus c1 plus c2 equals to 0 and substituting the values of c1 and c2. So, after simplification, this is the required equation of the surface x square plus y square minus z square minus 2x plus 4z equals to 0. Now, we shall develop an idea where we shall discuss how to find the system of surfaces which are orthogonal to a given system of surface. Suppose there is a one parameter system of surfaces, and this system is given by equation 5 f x y z equals to c, where c is a parameter. First, you note that the normal to this surface are proportional to del f del x, del f del y, del f del z, that we have already know. Now, the surface, if z equals to f x y is a surface such that it cut the system of surface 5 orthogonally, then the normal to this surface z equals to f x y, which are proportional to del z del x, del z del y minus 1, must be perpendicular to del f del x, del f del y, del f del z. So, using the condition of perpendicularity, we can obtain a relation del f del x into del z del x plus del f del y into del z del y plus del f del z into minus 1 equals to 0, or in other words, or with this notation capital P small p plus capital Q small q equals to capital R, where P, Q are assumed as del f del x, del f del y and del f del z. And we are interested to find the values of P, Q. That means, now we obtain a quasi-linear equation which is given in equation 6, and we want to find the solution of the quasi-linear equation 6. And we already know that the solution of the quasi-linear equation is related to the solution of a simultaneous equation which is known as Lagrange auxiliary equation, and this is written in equation number 7. dx by del f del x equals to dy by del f del y equals to dz by del f del z. So, solution of the equation 7 will give the solution of the quasi-linear equation which is written in 6, and that will be our required system of surfaces which are orthogonal to the given system of surfaces which is written in equation number 5. Now, we shall illustrate the idea taking one simple example. So, let us take this example. We have to find the equation of system of surfaces which cut orthogonally the cones of system x square plus y square plus z square equals to c x y, where c is a parameter. So, the equation, the auxiliary equation for the system of surfaces which are orthogonal to the given surface is dx by del f del x equals to dy by del f del y equals to dz by del f del z. So, these are the, so if we know the expression for capital F, so if we substitute these values, we obtain the simultaneous equation which is written here, and from this simultaneous equation one can obtain easily two integrals. So, one integral is x square plus y square plus z square equals to C1, and the another integral is x square minus y square by z square equals to C2. So, the general solution of this simultaneous equation, or not this simultaneous equation, the general solution of the quasi-linear equation is phi x square plus y square plus z square comma x square minus y square by z square equals to 0, or in explicit form one can write equation in this form x square plus y square plus z square equals to f of x square minus y square by z square. Now, we shall take another example to make the concept more clear. So, in this example we have to find the surfaces which intersect the given system of surfaces z into x plus y equals to c into 3z plus 1, where c is the arbitrary constant. That means we have to find the system of surfaces which cut this given system of surfaces orthogonally, and we have to find that surfaces which passes through the circle x square plus y square equals to 1 and z equals to 1. So, let us first try to find the system of orthogonal surfaces. So, for that, the given system of surfaces can be written in this form: f x y z is from the given system of surfaces. If we divide the left hand side by 3z plus 1, we obtain f x y z as z into x plus y divided by 3z plus 1 equals to c, where c is the parameter. So, if we vary the parameter c, we will get a system of surfaces. Now, the auxiliary equation for the orthogonal system of surfaces is given by dx by del f del x equals to dy by del f del y equals to dz by del f del z. Now, substituting the values of f from here, we can obtain the equations in this simplified form: dx by z equals to dy by z equals to 3z plus 1 into dz by dx plus y. And from this equation, one can obtain two integrals easily. One is dx minus dy equals to 0, that means after integrating we will get one integral x minus y equals to constant, and some manipulation of this equation will give the another integral. So, that can be obtained from this equation: x plus y into dx plus y minus 6z square plus 2z into dz equals to 0. Therefore, one integral is u, which is x minus y equals to c1, and the another integral is v, which is equals to x minus y whole square minus 2z square into 2z plus 1 equals to c2. Here c1, c2 are arbitrary constant. Now, we want to find that integral surface which passes through the given circle. Now, the parametric equation of the given circle can be written in this form: x equals to cos t, y equals to sin t, z equals to 1. So, if we substitute of x, y, z from this equation u equals to c1, we obtain this relation cos t minus sin t equals to c1, and if we substitute the values of x, y, z in the second integral v equals to c2, we obtain the another relation cos t plus sin t square minus 6 equals to c2. That is sin 2t equals to, so from these two equations, if we manipulate, one can obtain the value of sin 2t as 1 minus c1 square, and from the second equation the value of sin 2t can be obtained as 5 plus c2. So, from these two equations we can eliminate t to obtain a relation between the constant c1 and c2, like c1 square plus c2 plus 4 equals to 0. Now, if we substitute the values of c1, c2, where c1 is x minus y and c2 is written here the expression for v. So, if you substitute those values, we can obtain a function relation like this, So, this x square plus y square, after simplification we get that function as x square plus y square equals to 2z cube plus z square minus 2. So, this is our required integral, that means this is the system of integral surfaces which are orthogonal to the given system of surfaces, and it also passes through the given circle. Thus, in module 2 of chapter 2, we have discussed about a quasi-linear first order differential equation. We have defined that equation, we have derived the Lagrange auxiliary equation for a quasi-linear equation, and we discussed about the geometrical interpretation of that quasi-linear equation, and lastly we apply the idea of solving a quasi-linear differential equation to solve some geometrical problems. So, in this way we end this module of chapter 2.